Now we'll take up the fourth topic. Influence line diagrams for forces in the members of trusses. In the members of, we can add determinate trusses. Forces in the members of statically determinate trusses. This we want to take up now. Now then, what is the influence line diagram? Influence line diagram means it is a graphical representation of variation of reaction, shear force or bending moment, whatever quantity we take it, as a unit load moves from one end to the other end of a structure. How a unit load influences reaction or shear force or bending moment when it is moving from one end to the other end. If you plot that variation as a graph, or if you plot the influence as a graph, we call it as influence line diagram. Okay, so ILD means it is a graphical representation of variation of reaction, shear force, bending moment, etc., as a unit load moves from one end to the other end of a structure. This unit load has no unit, simply one. That quantity is moving from one end to the other end. Why should it move as a one unit load only? It is from the Betti's reciprocal work theorem. We get that. We see later on why we should take unit load. Why not some other load moving from one end to the other end? We'll discuss that point once the basics are understood. I'll go back to more fundamentals into that. Now, as a unit load is moving from one end to the other end, how that fellow influences the reaction? If you draw that influence as a graph, we call it as influence line diagram. Okay, so why should we draw such diagrams is the purpose of drawing influence line diagrams is if we know what is the influence of one when it is moving, when actual loads are moving, say supposing that 20 kilonewton is moving, then we can find the influence of 20 kilonewton easily. It is like linear interpolation. If one produces so much influence, 20 kilonewton produces how much influence? We can find from the linear interpolation. Linear interpolation, once you are making, implies that this influence line diagram concept are applicable to linear elastic structures only. Okay, so we are dealing with now linear elastic structures only, where if you know influence of 1, influence of 10 will be linear interpolation. You can linearly interpolate only when you have a linear elastic structure. Okay, next, what is the purpose of the influence line diagrams? If you take the bridge structures, there the loads move from one end to the other end continuously. When the cars, buses, trains, when they are moving from one end to the other end, at suppose reaction you want to find, say, for what position of the load you get maximum reaction. If you know the worst effect, that means maximum reaction at what position, if you know it, then for that reaction, if you design the support, then for any other position of loads, you will get the less reaction only automatically. The pair or column, whatever you are designing, automatically it will be safe. At a point, supposing that you want to design a section, loads are moving from one end to the other end. For what portion of the loading, bending moment at a given section is maximum? If you know what is the maximum bending moment that is likely to come, and you design for that maximum bending moment that particular cross section, then when the loads are moving at some other location, automatically cross section will be safe because you get less influence only. So that is the purpose of that. For what positions of the loads you will get the worst effect of shear force or reaction or bending moment. If you know that, and you can easily design for that worst effect, other loading conditions it will be automatically safe. Then whether the second purpose is if the loads are moving, sometimes what happens, the structures will be subjected to reversal of loads. Depending on the position of the load, force in the member or in the truss member can change to tension to compression. Whether it will change compression to tension or not, we have to first find is there any stress reversal or not for any position of loading. Then accordingly fatigue effect also we have to take into account while designing the members. So this information you will get from the influence line diagrams. Okay, that is the purpose of drawing the influence line diagram. As an introduction, we will draw influence line diagrams first for determinate structures. We will take first simply supported beams, then cantilever beams, then we will take the determinate trusses. That means first beams, determinate beams, then determinate trusses. Then we will take up after this indeterminate structures. Okay, so that is the scope. First simply supported beams we will take it. ILD for reaction at any support in a simply supported beam. First we'll discuss the simply supported beams, then we go for the cantilever beams, that means overhang portions. Assume that we have a simply supported beam like this. This point let us say A, B, length is say L. Assume also now that there is a small canal, not big river, canal is flowing. On the two banks of the canal, you took constructed two pairs. On the two pairs, you have kept a T-beam, let us say. It is like a T-beam simply supported bridge. And vehicles move this way or this way. As the loads are moving from one end to the other end, how that load influences the reaction we want to find. Here, this reaction is VA. This reaction, let us say VB. As a physical interpretation, when the unit load is on the ground, say this one, it has no units, simply one, that's all. If that load is on the ground, entire load is taken by the ground itself. Bridge will not take any load, it simply keeps quiet. The influence of one on the bridge will not be there. Now, supposing this is a unit load, is a movable load, let us say. Now, ask the driver to move over the bridge. Whether they give this ground in the exam or not, you must visualize that whether it is a beam or continuous beam, at the ends there must be ground level. So that means vehicles come, enter the bridge, leave the bridge. Same level should be there. They cannot be at two different levels. If ground is here, bridge is here, say, then vehicles come here, stop there. Then what you have to do to go to the bridge? You have to take a crane and lift the car or bus. You have to give it here, and it will come up to here. Then lift, use one more crane, lift it, pull it down, then it will go. Nobody will do like that. Lifting the buses and cranes, buses and cars with the help of cranes, lifting it, not possible. So ground level, beam level must be same. Whether they give it or not, you must assume that at the two ends there is a ground is drawn for bridge structures, say. So now this load, let us see, first we will take up the strength of materials concept, how we have to build the influence line diagram for reaction at A. Then we will try to simplify. So supposing that if the load comes here exactly at A, now we know what is VA. VA is 1 from strength of materials you have studied. So when the load is exactly at the support, entire load directly transfers to the support, beam will not take and transfer. Okay, so direct transfer of the load. That's what you have learned in SM. So VA is 1. Now when the load comes here, exactly at center, let us say, then what happens? First beam will take and transfer to the two supports. 50% is transferred here, remaining 50% is transferred here. That's how it is distributed. Now when the load is exactly at center, we know VA from equations of equilibrium point of view. VA into L minus 1 into L by 2. So VA is 0.5. So we know from strength of materials, when the load is at center, what is VA? Ask the driver to move forward. If V load comes exactly at the support B, then entire load is taken by VB. Then what is VA? 0. Now you see, you will find that as the load is moving from A to C to B, the reaction at A is continuously changing from 1 to zero point 0.5 to 0. If you plot that variation as a graph, that is called influence line diagram. See here, when load is here, the influence of 1 on VA is 1, that means 100%. When the unit load is here, the influence of 1 on VA is 0.5. We have to read like that. So this is 0.5. When the load is here, VA is 0. We have learned from SM. Now we read the same thing. The influence of 1 when it is at B, okay, the influence of 1 on VA is 0%. So VA you got 0. So we write it as ordinate, will keep it as 0. So those influences you plot it. We know when load is there, reactions Wx by L, we know. X has power 1 means it varies linearly. So the influence will go something like this. This is what we have learnt. This is a straight line. So it is a straight line linear variation plus. This is influence line diagram for VA. See, for the sake of, this is how it influences. This ordinate here it is 0.5. The ordinate is 0. Here ordinate is 1. Okay. Now, for the sake of a simple beam, for a simply supported beam itself, to draw this 3 times we have to find the reaction set A using our strength of materials or equilibrium equations. To save our time for a determinate structures, there is one person called Muller Breslau. They have given one easiest way of plotting the influence line diagram by taking the help of Betti's reciprocal work theorem, or we can say the principle of virtual work. Okay, let us see how what they did was, if any structure which is in equilibrium like this, then remove the support. Why, if you want to find the reaction at A, remove the reaction at A and apply unit displacement. That unit displacement is virtual displacement, means an imaginary displacement. Then the deflected shape of the beam itself is the influence line diagram for reaction at A. Okay, so this is what he has done. From Muller Breslau's principle. The basis for this one, once when we take again for the indeterminate structures, I will explain that same thing is applicable to everywhere. So this is what he says: to draw ILD for reaction at any support, remove the support and apply unit displacement. This is again unit virtual displacement. Actually, no displacement can happen. So, an imaginary displacement we will give it. Why we should give imaginary displacement? One is any structure which is in equilibrium. If we want to use from the principle of virtual work to find the forces necessary to keep them in equilibrium, we use the principle of virtual work in the engineering mechanics. Sirs might have told you, principle of virtual work will give you additional equilibrium equations. So, additional equations to solve the problems quickly. So, what we have done was, if any structure which is in equilibrium, apply virtual displacement, then total virtual work done is equal to 0. From that principle, you will know what is the force necessary to keep a structure in equilibrium. So is the case here. Remove the support and apply virtual displacement and find the virtual work done by all forces, equate it to 0. So from that you will know what is VA. So that's why here also we take it like this. Remove the support and apply unit displacement. Then the deflected shape of the beam itself is the ILD for vertical reaction at A. What is the basis that this comes from? This is from principle of virtual work. This is what you have studied in first year engineering mechanics. Supposing that you have a simply supported beam, let us say AB, length is say L. Some load W is there. Now, to find the reaction at A, what we do is you give a virtual displacement. This is a 1. This is the deflected shape of the beam. This distance, let us say now some value y. Now, from the principle of virtual work, total virtual work done is equal to 0. So, this VA is acting upward, displacement is also upward. So, work done by VA is VA into 1. W is acting downward, but displacement is upward, minus W into Y is equal to 0. So, VA you will get W into Y. This is the reaction rate. This is what you have taken in strength of materials or in the principle of virtual work. Supposing that if W also becomes 1, let us say, then VA becomes Y. See, reaction rate here becomes the ordinate. That ordinate we call it as influence. So, influence of W on VA is Y. Okay. So, that is how the reaction, that means for a unit load the influence is Y. This is called principle of virtual work. Muller Bresla has taken that principle of virtual work and he has given his statement. The deflected shape of the beam itself directly gives you the influence line diagram for reaction at A. Supposing that load is here say, then this displacement only you have to take it. That means wherever load is there, corresponding displacement only you have to take it and find the reaction. That displacement is now nothing but when you lift it, the deflected shape of the beam itself now becomes the influence for the reaction at A. So that's how he has derived this statement from this equation. Okay. So deflected shape of the beam itself is the ILD for VA. Now you understood how that statement comes. Then later on for deformed structures, we will take the Betti's theorem to prove why it is applicable to indeterminate structures also. But whether it is determinate structure or indeterminate structure, it must be linear elastic structure only. Otherwise, that linear interpolation you cannot make it. If 1 is moving, y is the displacement, 10 kilonewton is moving, how much it is. That type of linear interpolation is valid only for linear elastic structures. So your Muller-Breslas principle is applicable to linear elastic structures only, because your Bettis theorem is also applicable to linear elastic structures only, and this theorem, Muller-Breslas theorem, is derived from Bettis reciprocal work theorem. So accordingly, linear elastic structures only you can apply. Such linear elastic structure you have taken simply supported beam first. So now you understood how it goes. Now you see, this much work we will not do for finding the vertical reaction at B. To draw ILD for reaction at B, what we do is, this the simply supported beam, say support is here, support here. If you want to draw ILD for VB, remove the support, hold it, lift it by 1. Then the deflected shape of the beam itself is the ILD for VB. Now you see, this is the original position. Without removing the support at A, remove the support at B and apply unit displacement 1. Then the deflected shape of the beam itself is the ILD for VB, like this. This is ILD for VB. Okay. So that's how the influence line diagram is drawn. This the U means principle of virtual work, means total virtual work done. This is the principle of virtual work. Okay. So ILD for VA, ILD for VB we have drawn. Now having understood this one, how to draw ILDs, now let us see how numericals come in the exam. I remove this one. Now let us see how the questions come. Draw ILD for VA, VB and VD. In the exam, any one they will ask. Assume that you have a continuous beam This is the beam, let us say A, B, C, D. This, let us assume that this length is say 4 meters, 3 meters, 2 meters. Okay. This, if you show any circle at the intermediate location, it is the internal floating hinge. This is called internal floating hinge. At the internal floating hinge, what will be there? At the internal floating hinge, there is a pin. ABC is a single member, like this is there. So ABC is a single member, point A here, B is somewhere here, C is here. Then CD member, another member, you overlap it, Then assume that they are overlapped like this. Take a drill bit, make a hole into the finger, then insert one bolt, keep a nut here. That type of connection will be there at C. Now why we call it as a floating hinge? If you apply vertically downward load, it can go down like this. Lift it up, it will go up like this. Pull it, it will not come because there is a bolt. Because the hinge is within the structure, it is called internal. Because the hinge can move up and down, it is called floating hinge. So it is internal and also floating hinge. This is hinge but not floating. It is simply stays fixed in position like that. So that's why it is internal floating hinge. Can move up and down in case without any movement developed freely, it will go down or up. Okay, that's why it is called floating hinge. Now we want to draw influence line diagram for VA, VB, VD. For that what we do is, first reference line, the beam as is will draw. I want to draw ILD for VA. So remove the support at A and lift it by unit displacement. Then the deflected shape of the beam itself is the ILD for VA. In the process, we should not lift the beam at B and D, as in the fundamental I have told you. So don't lift the beam at B, don't lift the beam at D. Remove the support at A. If you don't remove the support at A, even the virtual displacement is also not possible. But you have used virtual work, that's why you have to lift it by unit displacement. Assume that you have displaced it by 1. Then the deflected shape of the beam is the influence line diagram. Such influence line diagram must always be a straight line, because in a statically determinate structure, the number of reactions are just sufficient to keep it in equilibrium. If any one support reaction you remove, then the structure becomes unstable. That means the structure becomes mechanism. Remove the support, it is now becomes a mechanism. In a mechanism, if you apply unit displacement, it undergoes rigid body translation or rigid body rotation. That means without any deformations, they rotate as a rigid body or they will translate as a rigid body. So, in a statically determinate structure, ILDs for reaction or shear force or bending moment are always straight lines. For that matter, any statically determinate structure you take it, whatever quantity you draw for the force quantities, it will be straight line only. Okay, so if I this you have to visualize like this. Send this point where I am holding is B, say. This point is A. This point is C. A, B, C is a single beam. At C, their CD member, another member is connected here and it is free to come up and down. So at B actually single beam, roller is here like this. If gap is there like this, say, then you have to weld a triangular plate here. Here also you have to weld a triangular plate. One base plate you have to weld it. Below the base plate only will be there. There is no pin here. At B, no pin. If there is a pin, you could have put a circle. If you don't put a circle, that means there is no pin. At intermediate supports of a continuous beam, we don't keep any pins. Single beam only will run. So only at B, you can bend the beam also. You have a simply supported overhanging beams. In the overhang beam is there means continuous member only, but simply roller support will be there. That overhang bends. For the overhang to bend, there should not be any pin in the beam. If pin is there, it will fall down. So if pin is there here, it will simply fall down. That means rigid body mechanism will happen. So ABC is a single member. So now I am that representation, now I am holding it here. ABC, now I didn't break the beam. Now remove the support at A, lift it like this. So A to B to C, it is a straight line, goes down. That we have to show like this, straight line. This is a straight line. Okay, this is positive. This member goes below, so you have to take it as negative. There is a floating hinge here. it permits the downward displacement. So straight line came. Now D here, this is C is going down, then CD member will simply come down like this, like this. Okay. So positive, if a beam goes above reference line, it is positive. If it goes below, it is negative. Now this is from linear interpolation, you can find the ordinates. For 4 meters it is 1, for 3 meters it is 3 by 4 or say 0.75. So this is your influence line diagram for VA. How we have drawn? Without removing the supports at B and D, remove the support at A and apply unit displacement. The deflected shape of the beam is ILD for VA. So that at later stages you get doubt how we have drawn, you read this one, you will know how we have drawn. Now what is the implication of this one? I told you whether they give you the here anything or not, you must idealize or you must visualize that there must be a ground here, there is a ground here. Now ABCD is a bridge, let us say. What this diagram tells you how to read this one is, when the unit load enters the bridge, the influence of unit load, that means when the load is here, the influence of unit load on VA is 100%. Because this entire diagram is for VA only. From this diagram, other than the reaction at A, no other information you can get. Now, when the load is here, his influence on VA is 100%. As the load is moving from A to B, his influence on VA gradually reduces to 0. When the load moves further right side, the influence of unit load on VA is negative. That means opposite to the direction of VA. Initially you have taken VA upward. Now VA will not act upward, VA will act downward. You see here, when the load is here, say, then it will try to go up, but the pin there will hold it and pull him down. So reaction will act downward. That represents below reference line. And as the load is moving from B to C, that negative reaction magnitude continuously increases. When the load is exactly at C, his influence on VA is 75% minus. So minus 0.75. That means if you put 10 kilonewton say, then reaction is 7.5 kilonewton down. Now, further if it moves right side, then his influence on VA gradually reduces to 0. When the load crosses the bridge and goes to the ground, no influence at all, nothing will be there. Now you see, this diagram tells you for some position of the load reaction is upward, for some position of the load the reaction is downward. In a day, supposing that 1000 times buses moved from A to D, and also 1000 times buses move like this, 1000 times buses move like this, say. So total 2000 times in a day. That means if you take a pin here, there is, I told you yesterday, last class, that there is a pin. That pin is subjected to, when the load is in the portion AB, the reaction is upward. That means shear force on the pin, double shear, I told you. The double shear is upward. When the load crosses, shear force is downward. So 2000 times in a day, shear force acts upward, downward, upward, downward. That means the pin that you are providing there is subjected to reversal of stresses. Reversal of stresses means direction changes, first upward then downward. If any material is subjected to reversal of stresses, reversal can be upward, downward, tension, compression. Direction must change. Then it is subjected, we say that it is subjected to fatigue. Fatigue means what? Any material subjected to reversal of stresses, it loses its strength. The property of losing the strength, we call it as fatigue. So it will fail quickly. So when you are designing that pin, supposing that you are designing this bridge for 100 years, then you have to say in 100 years maybe it is 10 million times, so reversal, stress reversal can happen. So accordingly for 10 million times, what is the fatigue coefficient? You will take it. Then accordingly you put, say you require ordinary circumstances 125 diameter pin, say. Now you may have, because you have to take care of the reversal effect also, instead of 125 pin you have to put 150 pin. So thick pin, so thick diameter pin you have to insert. So slide, to know whether it is subjected to stress reversal or not, first you have to draw ILD. This ILD will tell you whether it is subjected to reversal of stress or not. The support at A, it is subjected to stress reversal. That means pin is subjected to stress reversal. You must design the pin for that. Okay. So such information you will know. When the load is here, you will get maximum upward reaction. So intensity of load, standard loads are there. Bus IRS gives you standard class A type, AA type loading. So loadings are fixed magnitude. For that given loading position, what's the maximum upward reaction? When the loads are here, what's the maximum downward reaction? Then if you know what is the maximum upward and downward reactions, design that pin for that. Then for any other position of loading, automatically it will be safe. Once you design it for the worst effect, other effects automatically it will take care. So that is the reason why we draw influence line diagrams. Now ILD for VB we want, see here, ILD for vertical reaction at B. Now in this case, without removing the support at A, support at D, remove the support at B and apply unit displacement like this. Then the deflected shape of the beam itself is the ILD for VB. Take here, this point where I am holding the duster with my fingers is A, where with my black pen I am holding it is B. This point is a C, that end is C. Then CD member also was there. Only ABC first let us deal. Remove the pen, then it becomes unstable. Any statically determinate structure, removing the support means it becomes unstable. Such unstable structures, you apply unit displacement as rigid body, it will displace. So it has to be only straight line. No curved lines will be there for statically determinate structure when you are dealing with the reaction, shear force, bending moment. But for determinate structures, if you draw ILD for deflections for point loads is a third degree curves you get, then third degree curves only you will get for the deflections, even if unit load moves. ILD for deflections also can be drawn, that we will see later. What type, how much degree curve you will get. Now we are dealing with the forces and they have to be straight lines. Okay. Now A, where I am holding is B, this is C. Remove the support, hold it, lift it by 1 like this. Now A to B to C, it is simply straight line. So it will simply go like this. No bending. So since ABC is single member, in between you should not bend them or break them, because it will undergo rigid body displacement only. So smoothly like a pen you take it when you are again experimenting. Take a pen, what are all the positions we have to hold them, then lift it without bending the pen or breaking the pen. Whatever shape that pen takes, that is the influence line diagram. So there is a pin here. Now this portion simply comes down, positive. Everything is simply it goes up. This ordinate is 1. See, for 4 meters 1, for 7 meters 7 by 4, linear interpolation. That's all. This influence line diagram tells you that if you want to get maximum reaction at B, you must load in the overhang portion. In strength of materials also you have studied the same thing. If you have an overhanging beam, single overhanging, if you put the load on the overhang portion, supporting the overhang, there is a the support which supports the overhang, their maximum reaction will get. Far end, the simply support, there is a downward reaction, maybe less, whatever it is, but the overhang side support will have more reaction than the applied load itself. Now you see here, 7 by 4 means 1.75. That means if you apply 10 kilonewton here, the reaction at B is 17.5 kilonewton. More than the applied load, you will get the reaction. Okay. In steel also, you will get such type of things. Prying actions are there. Design of steel structures, again I will explain. Their prying actions we learn. That is prying action when you are pulling a member. Then the overhangs will, they will try to go up, but if the supporting plate push him down, say, then what will happen? The bolt load, if you apply 10 kilonewton, bolt load will be, each bolt will take, 2 bolts are there, 10 kilonewton you apply, 5 supposed to take. Instead of 5, they will take 7 kilonewton because of the same reason. See, penultimate support, here you see, when you apply load here, say, it is supposed to go down. If it is going down, this should go up. If you don't permit this go up, I have to pull it down. Then here the reaction is more. That additional force in steel structures, we call it as prying action. So those prying actions, again, when we take up steel structures, I'll again explain with these examples how we have to make it. Okay, how many ways the T sections, etc., they will fail. We see the prying member design, whether they are safe or not, also we have to discuss. That means the observation of this we apply in the design of steel structures also. In the plastic analysis of the beams, there we analyze when the design is coming, then same thing we extend it to the design. But the basis of the plastic analysis and design also comes from the strength of materials. This is actually strength of materials. Okay, when you are revising, first strength of materials, then steel structural analysis, then steel structures, at a stretch you go through them, then completeness will be there. Entire structures you feel that you have completely understood. Okay, that is the sequence you must follow. Okay, now you see 7 by 1.75. This is what you have learned in SM. Here also ILD also comes like this. Put the loads in this zone, you will get reaction at B maximum. And load somewhere here means reaction at B is relatively less. So this is ILD for VB. Then ILD for VD, vertical reaction at D. Here there is VB, there is VD. If I want to draw ILD for reaction at D, ILD for reaction at D, ILD for VD. What is the process? When you are drawing ILD for VD, you should not remove the support at A and B. Without removing the supports at A and B, remove the support at D, hold it, lift it by 1. Then the deflected shape of the beam itself is the ILD for VD. So don't lift the beam at A, don't lift it here. Here you give unit displacement, the deflected shape. Now you see, when you lift there by 1, A and B cannot be lifted. See here, this is the beam, let us say. Where I am holding is A, this is B. This point is a C. At two positions, I hold it tight like this. Don't permit the beam to lift it at A and B locations. Can C be lifted up? Without bending or breaking, I cannot lift C because I am holding at two locations like this. Then this cannot be lifted. Okay, and instead, if you have to lift it means I must bend it, which we should not do. Why we should not do? Because in a determinate structure, removing the support implies that it is unstable. Then any rigid body displacements only you have to draw. Principle of virtual work for the statically determinate structures is that removing the support implies that it undergoes rigid body translation or rigid body rotation. So engineering mechanics, that's how we have taken for that. Then for the deformable bodies, what we have to do? Then we take the help of Betti's reciprocal work theorem and prove that Maxwell's and prove that this uh, Muller-Breslas principle can also be applied to statically indeterminate structures, but they must be linearly elastic. Okay, those two helps with it. Now we are taking the help of virtual work. So at this point now, because A and B cannot be lifted, that implies that C also cannot be lifted. Then C here, D here. Remove the support at D and apply unit displacement like this. Then that is the deflected shape of the beam like this. Plus, that's all. That means as the load is moving from A to B to C, his influence on reaction at D is nil. See here, reaction is 0. But once load crosses C, his influence on reaction at D is like this. When the unit load is at D, his influence on VD is 100%. When the load crosses, everything is over. So, this is what is the process. Without removing the supports, without removing the supports at A and B, remove the support at D and apply unit displacement. The deflected shape of the beam, itself is the ILD for VD. You see here why it comes like this is, assume that load is somewhere here. Load is 1, I want to find VD. Strength of materials, what you have done, if load is here, say, here floating hinge, bending moment at C is 0. So bending moment at C is 0 means stand at C, look one side. You can see left side or right side, but not both sides. If you see both sides of the section, it is equilibrium equation. External effects you will get sigma m is equal to 0 means moments of all forces acting on the structure must be equal to 0. If you see only one side, you will see the internal effect called bending moment, how much it bends. That's why I have studied in bending moment diagram, bending moment definition. Bending moment at any section is defined as the uh, moments of all forces acting on LHS or RHS of a section only. Only then you will get that internal effect. Okay. So VD into 2. You see here, bending moment at C is equal to 0. What will get? VD into 2 is equal to 0. 2 can't be 0, so VD is 0. So for all positions of the load from A to B to C, I'll stand here, look right side, VD into 2 is 0, so VD has to be 0. That much headache we don't have to do it, just hold it, lift it, it will also tell you the same thing. In the exam, any question comes in the strength of materials also to find what is the reaction for any loading, for bending moment or shear force. First check whether you can draw ILD for that quantity and solve the problem. Numerically, if you want to take, assume that it takes say 3 minutes time. But if you solve it by taking the help of influence line diagram to find the reaction or shear force or bending moment, it takes only 30 seconds time. That means at least 6 times time you can save. We will see with the examples also in the later stages how you must save the time. Okay, so this is ILD for VD. Now let us see the next question. Next one, two wheel loads 10 kilonewton and 5 kilonewton spaced 2 meters apart crosses a simply supported beam of span 10 meters. Maximum reaction is. How to find that maximum reaction? Based on the description, first you must draw the diagram. 5 kilonewton, this is 10 kilonewton, spaced 2 meters apart. Now you have a simply supported beam whose span is 10 meters. A, B. He didn't give you to find uh, VA or VB. That means it is our choice. You can find VA or VB, but it should be maximum. And assume that there is a ground here. Here also ground. ILD for VA, if you draw, this is 1 plus, okay. This is ILD for VA, we know. If you want to find maximum reaction, first you have to draw ILD for that reaction. That ILD will tell you where you have to keep the loads to get the maximum reaction. Always at the maximum coefficient level, keep the maximum load also. Maximum load into maximum ordinate, you will get naturally maximum. So like that you have to manage. Greater load, greater ordinate, lesser load on the span. So we will keep 10 kilonewton load here, 5 kilonewton load here, spaced 2 meters, like this. You will get maximum load, maximum reaction. If more than 2 point loads are there, 4 or 5 loads are moving, then textbooks give you condition load by the succeeding wheel space divided by total load by total span. It should be greater. Those conditions, they are only necessary conditions but not sufficient conditions. So that based on that condition, you will never get maximum. You have to check all the possibilities. Anyhow, we have to check all possibilities. Then you don't have to check that condition whether it is satisfying or not and waste our time. One by one, you will move them. Whatever value, it will take hardly, it will take say 1 minute, 1.5 minute time. You don't have to use any condition and get. Condition will not help us because after satisfying condition also you will get, you may not get correct one because there is only necessary one but not sufficient one. So load by succeeding wheel space should be greater than the total load on the span, remaining load on the span by the span. It should be greater. That is a necessary one, but not sufficient. That means you have to again check for the second load also. So also that conditions I am not giving you because in the stipulated 30 seconds or 1 minute time, you cannot check. You have to do only this way. First possibility, this one. Then second possibility is this one. Then one by one we'll move it. Within 2 attempts, you will get the correct result. In this case, 2 attempts also are not required. By inspection, you will know greater load, greater alternate, lesser load span. That's it. Okay. Like that, in the exam, the questions will be given such that no question takes more than 30 seconds time or at the most 1 minute time if you have to calculate. Those calculations also will be over in 2 lines. If you are writing more than 2 lines or 3 lines means that that is not the way of doing the problem because they don't let you hurt by taking too much of calculation or too much of thinking. The purpose of GATE or engineering services is not to check your numerical capabilities. Only your conceptual capabilities only they will check. So no great calculations, no great thinking will be there in these 2 exams. Okay. Now coming to this one. This value is 0.8 now because 10 meters 1, 8 meters. This distance is 8 meters. Linear interpolation. So now you will get VA. So to get maximum reaction, keep the loads as shown in figure. So maximum reaction you will get. Ten into 1, load into his influence. Where whatever load you keep it at A, his influence on VA is 100%. Then influence of 5 kilonewton on VA is only 80%. Then where will 20% go? The 20% of 5 kilonewton will go will be taken by some other fellow. Who will take? In this case VB, but this diagram will not tell you who will take the other 20%. This diagram tells you only about VA, no other information you can get from this diagram. So, influence of 5 on VA is only 80%, so you have to write that one. Load into his influence only 80%, so 0.8. So, 14 kilonewton. Any other position of the loads, you will get less than 14 kilonewton reaction. Okay. Now, we'll see the next problem. In the above problem, if a UDL, uniformly distributed load of 5 kilonewtons per meter width, this 5 kilonewtons per unit width and length 3 meters, crosses the beam, find maximum reaction. Now, it's like this. This is now a simply supported beam, 10 meters span. This is the influence line diagram. 1, plus this is influence line diagram for VA. Now, how to keep the UDL? That uniformly distributed load, you must keep it at the greater influence. This value is 5 kilonewtons per unit width and length is 3 meters, like this. Okay. In SM, this is what you have studied. Uniformly distributed loads are like this. A, B, let us say. Like this, we will show. Uniformly distributed load can be idealized as infinite number of point loads. This is W kilonewtons per meter width and length 3 meters. This W kilonewtons per meter width per unit width, what do you call this one? W kilonewtons per unit width, it is called intensity. It is called intensity of UDL. Now assume that this beam width is say 1 meter width. On 1 meter width, if you take again say, actually supposing that 3 meters is there, that beam width is 3 meters and load is say 2 kilonewtons per meter square is acting. So 2 kilonewtons per meter square means per unit width how much? 2 kilonewton per meter square into 3 meters. So 6 kilonewtons per meter. So if I take 1 meter here, on this 1 meter length, there is a load of 6 kilonewton. Means 6 kilonewton per unit width it will act. So width of the beam is now 1 meter. On that beam, the width of the sub beam is 1 meter and load is acting over a length of say 3 meters. Maybe overhang was there. That entire thing will act on the beam only. So per unit width means unit width of the beam, there is a load of 6 kilonewton. That 6 kilonewton, you call it as intensity of UDL. That 6, 6, 6, 6, everywhere 6 will be there. Okay. Now, that is like a, you can idealize that uniformly distributed load as infinite number of point loads of same magnitude W. So, everywhere W, 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 W will be there. Okay. That is the meaning of that. Is generally instead of writing what we do is W kilonewtons per meter width, we remove it per meter width because it is understood. So W kilonewton per meter you write it, that per meter there is a length. So W kilonewton per meter width is understood. So every time we don't have to write, so we leave it that way. Then this is the displacement diagram, virtual displacement diagram. It is 1 here. This value, say if it is 1 means here it is 0.7 because this length is 7 meters. For 10 meters 1, 7 meters 0.7. So this value let us say 0.7. Now I told this UDL can be treated as infinite number of point loads. Now force into displacement, virtual displacement gives you work done, virtual work done. So W into 1, next W into not one's lesser value. So work done, what is virtual work means, you will calculate the virtual work done, force into displacement. So W into 1, this W into lesser value, this W into lesser one, less, like this. As the loads come closer, the lines also come closer. In a limiting case, as you draw lines the closer and closer, it looks like area. So we write it as intensity of UDL into area of the displacement diagram gives you work done, virtual work done. Now here instead of writing area of the displacement diagram, you will write it as area of the influence line diagram. Influence line diagram is nothing but the displacement diagram. How the beam displaces, that displacements only you have drawn. So UDL can be treated as infinite number of point loads. Once they ask this as a 2 marks question. So VA is equal to intensity of UDL, that means W kilonewtons per unit width, into area of ILD or area of the displacement diagram. Area of ILD under UDL. This is the form. That's how the work done formulas you have calculated in first year engineering mechanics. Okay. When UDL is moving, when UDL is there, work done, how we calculate intensity into area of the displacement diagram. Here also same thing. We call the displacement diagram as influence line diagram. So now VA is nothing but intensity of load 5 kilonewtons per meter into area of the influence line diagram. Area of the trapezium 1 plus A plus B by 2 into H. Intensity of UDL, area of ILD. This is area of ILD under UDL. This is intensity. Okay. Now you will get this value as 12.75, 12.75 kilonewton. Okay. Now supposing that in your calculations earlier you have calculated this way. If you have a uniformly varying load, let us assume, like this load is there. Now you see this is W kilonewtons per meter width. This is called intensity. This is W kilonewton per meter length. We should not read, because if you move by a length of 1 meter say, then W will not be equal to W. Here W is there, kilonewtons per meter length you read suppose, but after 1 meter what is intensity? Not W. That means it cannot be W kilonewtons per meter length. This is per unit width is so much, then that is called intensity. It in this that intensity is gradually reducing to 0. That's why it is called uniformly varying load. If same intensity is there, then you call it as uniformly distributed load. Intensity is distributed uniformly throughout the length. So the UDA, the uniformly varying load, this goes like this. It varies from W kilonewtons per meter width. You have to read like this, and varies linearly to 0 at other end. Okay, like that. So now this point is cleared. Accordingly, you've calculated the reaction, shear force, bending moment, many things you have done. So when UDL is there, that's what you have to do it. You have to take the intensity into area of the displacement diagram. Uniformly varying loads they will not give you, because the load is varying, ILD is also varying say. Then you have to take a small strip and integrate. Once integration is there means more time only, nothing else extra. So they will not ask uniformly varying moving loads. Next. I remove this one. Next one. A train of how the one of the papers how they ask, let us see what is the scope now, how much time we have to spend. A train of two wheel loads 150 kilonewton and 100 kilonewton spaced 5 meters apart crosses the beam shown in figure. beam shown in figure from left to right. See, they are giving that in which direction the loads are moving. That is only just to save our time. Only one possibility you have to check. From left to right with 100 kilonewton load leading. Which load is also leading, they have told us. Then you don't have to reverse and check other possibilities. To prevent checking the other possibilities and wasting our time in the stipulated 2 minutes time, they give you which load is leading, which direction they are moving. So for that case only you have to check what is the maximum reaction or shear force or bending moment. Okay. During the passage of loads, maximum and minimum support reactions at support R. Like this they ask. Then they give you the options like this: 300 kilonewton and minus 30 kilonewton, 300 kilonewtons minus 25, 225 kilonewton minus 30, 225 kilonewtons minus 25. So like this they have given you the options also. Now you see minus values as minimum reactions they have given. That means they are mathematical minimum values, not your things. Whenever even in the, we'll see that part when I'm talking discuss, we'll take that. This is say 100 kilonewton is leading. This is say 150 kilonewton spaced 5 meters apart. It is moving on a beam like this. Okay, this is the beam they have given. This is a P Q R S. This length is 3 meters, 10 meters, 5 meters. This is the one. Maximum and minimum reactions at the support R we have to find. Then, where I told you whether they give it or not, you must assume that there is a ground here, here and also here. Okay. Now, support reaction at R means you must draw the influence line diagram at R. That ILD will tell you where you should keep the loads to get maximum and minimum support reactions. This is double overhanging beam but simply supported. Without removing the support at Q, remove the support at R and apply unit displacement. It will go like this. And when I lift it, this is the point, let us say. Like this I am holding it. This is P, Q. This is at the end, the extreme left end is P. Where I am holding is Q, R, S. Remove the support at R and lift it up like this. You see this P end is going down. So let it go down like this way. Okay, this is minus, this is plus. Now you see, for a distance of 10 meters, this height is 1. Then for a distance of 15 meters, it is 1.5. And for a distance of 10 meters, 1 means 3 meters, zero point 0.3. Minus, this is plus. This is ILD for vertical reaction at R. So first you have to draw ILD. This ILD will tell you where to keep load to get minimum reaction and also maximum reaction. So this 150 and 100 load system is going on the bridge. When they are moving, first who will enter the bridge? Here. First 100 will come here. When 100 enters the bridge, 150 will be here. 150 kilonewton, the spacing is around 5 meters. Okay, we'll keep it somewhere here. This is first possibility. First possibility. For this possibility, what is the reaction at R? We are 1. First possibility we are taking. 150 is on the ground, only 100 is there. Just enter the ground, enter the bridge. When front wheel enters the bridge, back tire is on the ground only. So this will have no influence on the reaction at R. So 100 into minus 0.3. So you will get minus 30 kilonewton. This is 150 into 0, you have to write it. So minus 30 it will get. Now ask the driver to move forward. Then he will go like this. Till 150 kilonewton enters the bridge, ask the driver to move forward. That means this fellow should move 5 meters. So 100 kilonewton, here it is 150 kilonewton. This is 5 meters. This is your second possibility. At this point, for 5 meters means 3 meters, 0.3. From here to here, 2 meters. So this value is 0.2. This is your second possibility. So we are vertical reaction are at second possibility. 150 into minus 0.3 plus 100 into plus 0.2 minus 45 plus 20 minus 25 you will get. This is the second possibility. This is the first possibility. Then what is the minimum reaction? Minus 30 or minus 25? Minus 30 is minimum, mathematical minimum. So that's what you have studied in the 6th class. 0 is here, minus 25, minus 30. Minus 30 is less than minus 25. That's what you have learned. So minus 30 is the minimum reaction. So we are minimum minus 30. Not only here, everywhere in the principal stresses, sir might have told you maximum and minimum principal stresses when you calculate. Maximum principal stress F1 is 0. Minimum principal stress F2 minus 30. Minus 30 is minimum and maximum is 0. That like that. Any element, whether steel or whatever element when you are taking, it need not fail because of major principal stress only. It can fail by minor principal stress also. Okay, so that's how that minus 30 also is the cause of the failure, right? Like that. So either here or SM, wherever if you say minimum means mathematical minimum, then if specifically if they mention if that minus values are not there, supposing that, then 0 also I can get minimum reaction. But the options will tell us how you should think about the problem. So if you get minus 25 minus 30 you have to answer. He's not worried what you will do with that minus 25 or minus 30. Minimum means mathematical minimum. Next, ask the driver to move forward to get the maximum reaction. When he is during the passage means he is now driving here. Assume that he has come up to here. This is 100. 100 comes here, 150 will be exactly on the support. This is first possibility. So we are 1. How much you will get? 150 into 1, 100 into 1.5. 150 into 1 plus 100 into 1.5. So you will get 300 kilonewton. In the first possibility, you get 300 kilonewton. Now ask the driver to move forward. Then what will happen? 100 will go to the ground somewhere here. 150 will come here. Again 5 meters. Now 100 has no influence because it went to the ground. So this is second possibility. Then what is VR2? 150 into 1.5. That's a plus 100 into 0. So 225. So what is the maximum reaction? So VR maximum, you will get 300 kilonewton. So during the passage of these two sets of load moving from left to right with 300 kilonewton with 100 kilonewton load leading, minimum reaction is minus 30, maximum reaction is plus 300. So accordingly your option is this one. This is the scope, the gate. It should be over in 2 minutes time in the exam. You see here, first possibility when you are checking it, you will check this minus 30, you got it. Then once it moves here, 100 here, and this also you have to check. Then once it is, by the time you draw this diagram, you become familiar with the diagram, even if you are doing it for the first time. When I keep it here, 100 into 1.5, 150 into 1, so 300 you get it. Then once it goes away, then this fellow will come, 150 into 1.5 is 225, so useless. You can read the problem itself. Because I am assuming that you are learning it for the first time, I have an entire thing explained and drawn. In the exam, if you can visualize how it looks like, this much first possibility, second possibility, you don't have to explain to anyone. Okay, so that's how the questions will come on the influence line diagrams for reactions. Now we will see how to draw influence line diagram for shear force at any section. ILD for shear force at any section C in simply supported spans. Cantilevers, it will be different. Simply supported spans we are discussing first. Now assume that we have a beam like this, A, B. There is a ground here, here also ground. Somewhere here, section C you have taken. This distance let us say A, this distance let us say B. Not necessarily L by 2, it is some value A. Total span is L. We want to find at any section C which is at a distance of A. First we will take what we have done in strength of materials. We will build it from fundamentals as in the reaction. From the fundamentals first we will build the ILD. Then let us see how Muller-Bresla has simplified that drawing of ILD. Muller-Breslas principle only we have to use in the exam, which will let you complete in 20 or 30 seconds time. No question of complete analysis. But first time when you are learning, I want to show you how they have to be drawn. Then we will increase the speed of drawing the diagrams. So VA, VB are the reactions. Unit load, suppose assume that somewhere here is there. When the load is here, we know how to find the reactions. So we assume that we have calculated the reactions. Now I want to find shear force at C. First case, ILD for shear force at C. First we will take up first point. Load is, unit load is somewhere between A and C. When unit load is somewhere between A and C, here, how to find shear force at C? What you have studied in strength of materials, if you want to find shear force at any section C, your first task is you must go and stand there at C. Now you have a choice to look left side or right side. Whichever side is easier, that side you will see and find the unbalanced vertical force and finish off the problem. That's all. So shear force sign convention we know. This is the beam, let us say. Section left side upward or right side downward, you will take it as positive shear force. Section left side downward or right side upward, you will take it as negative shear force. This is a sign convention you have studied. Same we will use. From these sign conventions only we draw influence line diagram. From the influence line diagram, sign conventions didn't come. Existing one, we are making use of that. So stand at C. Now you have a choice to look left or right. If I look left side, I have to deal with two forces. To avoid that headache, you look right side, only one force. Since you are sure that whether you look left side or right side, you will get the same result. Then you look at easier side, finish off the problem fast. Only to increase our speed of solving the problem, we are looking right side. But you have the choice of looking left side also. Shear force at C is equal to stand at C and look right. So section right side upward, section right side upward negative. So you will get minus VB. This is the shear force at C. But I don't want to draw shear force at C. I want to draw ILD for shear force at C. If I want to draw ILD for shear force at C, draw ILD for minus VB. That will tell you what shear force is because the sorry, because that is the expression you got it. So ILD for shear force at C is equal to is nothing but ILD for minus VB. So draw ILD for minus VB, it is nothing but ILD for shear force itself. But this expression is valid when the load is between A and C only. So draw ILD for minus VB and consider between A and C only. Why consider between A and C only? Only when the between load is between A and C, this expression is valid. Otherwise, some other expression I have to write. So we will draw like this. If we know how to draw ILD for VB, remove the support, lift it by 1. But now I don't want to draw ILD for VB, I want to draw ILD for minus VB. So instead of lifting it up, push it down like this. This value is VB, its value is 1. Then out of this one, you consider only up to here. This is minus. This only construction line it will become. This is we should not consider because this expression is not valid when the load is here. So that's why this we don't consider. So when the load is between A and C, this much influence line diagram is valid. So wherever load is there here between A and C, load into this ordinate will give you the reaction at B. That reaction at B is nothing but shear force at C. That's what we have learned in SM also. Now ask the driver to stand somewhere here. He'll move and stand somewhere here, say. Now take that point. Unit load is between C and B, say. Same load has moved here. Now if you want to find shear force at C, how you calculate? Now see same right side if I want to see, I can see, stand here, look right side. But two forces are there. 1 minus VB I have to write. Instead of writing plus 1 minus VB, 1 minus VB is nothing but VA. YNS radius I can directly look left side and get the same result. So if I see left side, this already gone here. So left side there is only one force VA. That's all is the shear force. So shear force at C now means stand at C and look left because it is easy for us to look left. Much easier if you see top, there is no load, but we should not look like that. You don't want to deal with one force also, let us say right side two forces, left side one force. Why headache? Let me look top or let me look bottom should not be done. Either left side of the beam or right side of the beam only. So stand at C, look left. Section left side upward. See here, section left side upward, positive shear force. So plus VA. So draw ILD for plus VA and consider between C and B only. Now you see, plus VA means remove the support, lift it by 1. So you lift it by 1 like this. Now somewhere here it will go. Okay. Out of this up to here only it is valid. This is plus. This is again construction line. So ILD for VA, this is 1. Now this is linear interpolation if we take it. For a distance of L, 1. For a distance of A, this value is A by L. Whereas here, for a distance of L1, for a distance of B, B by L. Now A by L plus B by L, total ordinate becomes 1. So everywhere this ordinate is 1 only. Okay. So this is the this is ILD for shear force at C. Now you see this diagram tells you like this. You want to draw ILD for shear force at C, say. Assume that you have a shear force measuring gauge, you stick it, you stand there. Ask the driver to move from one end to the other end. When he enters the bridge, shear force at C influence is 0. As he is moving towards the C, his influence on shear force is negative and its value is increasing. When he is just to the left hand side of C, shear force at C is negative and negative value is maximum. Once shear load crosses C, then suddenly shear force changes from negative to positive. Okay, then load into B by L is the shear force at C and its value is positive. As the load moves from C to B, his influence on shear force gradually reduces to 0. What happens when the load is exactly at C? If the load is exactly at C, shall I take B by L or A by L? Not defined. Anything we can take. Why should I take B by L or A by L? That's why in strength of materials you have studied, exactly under point load, shear force is not defined, or we can say shear force is indeterminate. Indeterminate means you don't know whether you have tried B by L or A by L. Same problem comes here. But actually, point loads means they have some width. So, from the left width to right width, strength of materials you have studied, that when it's going like this, actually small, that inclined line will be there. It's not vertical, some inclined. Some fashion it will vary, maybe linearly, parabolically, that small length. How it varies, we don't know. Okay, so we assume that it is like a sudden jump. Now we write as if shear force is indeterminate exactly under point load. Because where in that width, which side, which width you have taken? Width, let us say 10 mm. Over that you applied. In that 10 mm zone, whether you have taken from the 2 mm or 3 mm or 4 mm, we don't know. So accordingly it will vary. So we take it as undefined or indeterminate. Same problem comes here also. So what we do is we simply draw a vertical line. So this is ILD for shear force. Now let us see. In a day, assume that 1000 times buses moved from left to right. Then the cross section, when the load is coming up to here, shear force is negative. Load crosses, shear force is positive. That means the cross section is subjected to upward downward shear force. That means stress reversal will be there. So when you are designing, you must take the fatigue effect also into consideration because shear is changing its sign. Okay. Now, so accordingly we will design the sections, that is the different issue. Now it is in the exam a 2 marks question. You must complete in 1 minute time after reading and all. So this much story in the exam in 2 minutes time we cannot write. Load is left side, let me see right side. Load is right side, let me see left side. So we cannot do that part. So to save our time, Muller's principle we have to consider. So let us see how to consider characteristics of ILD for shear force at sea. Now you see, take this one. If I take this slope here, see clockwise it is rotating, theta A. Tan theta A is nothing but theta A, opposite side by adjacent side. So 1 by L. Here this slope, let us say theta B. You want to see that this is also rotating clockwise. This is also rotating clockwise. Opposite side by adjacent side, 1 by L. What's the total ordinate from here to here? It is 1. This is total ordinate is 1. Now you see how to get this deflected shape of the beam. What Muller said was, this from here we can first write the characteristics. Tan theta A is approximately equal to theta A is equal to 1 by L. Tan theta B is approximately equal to theta B is equal to 1 by L. So theta A is equal to theta B is equal to 1 by L. This what you have understood from the diagram. Then this is the first point, let us say. Second point is sum of ordinates. Sum of ordinates of ILD for shear force at sea. What will get? A by L plus B by L. I can write A plus B by L. A plus B is nothing but L by L is nothing but 1. These are the observations. Now let us see what Muller did was this one. From Muller, come to this one. To get this deflected shape of the beam, without removing the supports at A and B, cut the beam at C. Cutting the beam at C means releasing the shear force. Removing the reaction means releasing the support reaction. So release that quantity. Cut here, shear force is released. Once you cut here, it becomes unstable. Mechanism it becomes. Now whatever displacement you give it, the structure undergoes rigid body translation or rotation. So cut here, hold left piece, pull it down, right piece, lift it up like this. You tear it this way. You tear it such that theta A is equal to theta B is equal to 1 by L. Then ordinate automatically at C becomes 1. After cutting it separates, you connect with a link, small link, so that the deflected shape of the beam itself is the ILD for shear force at C. So that's what Muller says. Okay. Now from Muller, what he says is this one. Without removing the supports at A and B, cut the beam at C and lift the beam such that theta A is equal to theta B is equal to 1 by L. So that total ordinate at C is equal to 1. Okay. Then the deflected shape of the beam, the deflected shape of the beam itself is the ILD for shear force at C. Now this much story we will not take it in the exam. If they ask you ILD for shear force at C, say if it is a simply supported span, cut there, lift it. Then within 10-15 seconds you must close the problem. Remaining 1.5 minute you use it for some other problems. But you can complete in 10 seconds or 15 seconds only when you take the help of Muller. That means the process you should understand, then you can save time. You can increase the speed of solving the problems. Now, let us see how numericals should be solved. Okay. Now, let us see how questions will come on ILD for shear force. ILD for shear force at RHS of A is, assume that you are given a beam like this. Okay. This point, let us say A, B, C, D. This distance is L by 4, this is L, and this is L by 4. Okay. This is the reference line. RHS of M is just to the right hand side of A. Now, what is the process? ILD for shear force at RHS of A. What is the process? Without whatever we have written earlier, without removing the supports, without removing the supports at A and B, where you have to cut, because you are asked to find RHS of A, you must cut at RHS of A only. So without removing the supports at A and B, cut the beam at RHS of A and lift the beam such that theta A is equal to theta B is equal to 1 by L. Then the deflected shape of the beam itself is the ILD for shear force at RHS of A. This is the process. To draw this one, you have 2 minutes time. It's a 2 marks question. Okay. Now let us see how we have drawn the diagram for ILD for shear force at C. For all such problems, this is a reference for us. This is what we have drawn. The earlier problem A, B. If I want to draw ILD for shear force at C, this is A, this is B, and what you have drawn was like this. After cutting it, this I have to push it down, lift it up, minus plus. This is B by L, A by L. This is what you have done. Okay. This is our ILD for shear force at C. Coming to this one. Now RHS of A is a simply supported span. AB is also simply supported span. For such spans, this is the process. Now here A is there some 2 meters or 3 meters. If that C gradually goes to the left side, to the extent, limiting case is just to the right hand side of A I can go. If I take just to the right hand side of A, how much A will become? Approximately equal to 0. If not 0, approximately equal to 0, maybe 0.001 mm. So A becomes almost 0, B becomes almost equal to L. Now come to this one. If it becomes, now after that what we have done, what is theta A? I rotated clockwise. Theta A is 1 by L. Here also I rotated clockwise. Theta B is 1 by L. How to decide is, this is the initial position. At B you stand, this is the initial position. To get the blue color line, I have to rotate clockwise. I must look left and rotate clockwise. At A, this is the initial position. Beam is right side, so I have to look right, then clockwise, like that. So now come to this one. First what you have done here, without removing the supports at A and B, cut the beam at C. Without removing the supports at A and B, where you have to cut now? RHS of A. Cut the beam at RHS of A. Then lift the beam such that theta A is equal to theta B is equal to 1 by L. Now you see. As first assume that this AC overhang is not there. This pen where I am holding is say A. This is RHS of A. Maybe this length is 0.01 mm. Here I am cutting it. This length is 0.0. However small it is, but that much distance is there. Now that little piece I have to hold it and rotate clockwise, because I have to rotate clockwise. Why should I rotate clockwise? Because of shear force sign convention, we are forced to rotate clockwise. Why can't we rotate anti-clockwise? Then if you rotate anti-clockwise, entire strength of materials shear force sign convention you have to change. Because from SM sign conventions only we have drawn. So rotate clockwise. So however small it is, if I rotate this small piece clockwise like this, if overhang is not there, no issue, only this will come down. If overhang is there, it will go up. Let it go up. You wouldn't bend, you wouldn't break. After cutting it, once this beam, if you cut it, it becomes unstable. That unstable structure, if I rotate, it undergoes only rigid body rotation. So no curves will be there, straight lines only should be drawn. So that blue color line what you have drawn here, this is actually after this red color was there here. This is what you have drawn, blue and red. Now first blue color we are drawing. Rotate clockwise without removing the supports at A and B. You rotate clockwise. So actually it should go down like this. That this extended line I have shown so much, but actually it ends here only. But this fellow is going up. Let it go up like this. Plus it became. But actually it is, you have rotated clockwise. Theta A is equal to 1 by L. If you rotate 1 by L, this went up, so this also goes up, this is also theta A only. 1 by L into L by 4, 1 by 4. So theta A into L by 4 is nothing but 1 by L into L by 4. You will get 1 by 4. This 1 by 4 comes from that. So this blue color line, here also if at all there was overhang say, we could have extended that line. Overhang was not there, so we left it. So this part is over. Next this part. After cutting it, I rotate clockwise. After cutting it, I should rotate clockwise. When I rotate clockwise, just to the right hand side of A only. This is for clarity sake only have drawn, but the distance is 0.01 mm. So it is almost at A only. So 1. This also it will end here only, but clarity sake, what you have done, that construction I have shown. 1. Here it should be 0. So this will go something like this. Okay, this is plus. Now because you rotate this theta B is also 1 by L. If I rotate clockwise, this will go down. Let it go down. If overhang is not there, I will stop here only. This is also theta B, 1 by L. 1 by L into L by 4, 1 by 4. So this is 1. This quantity is minus, like that. This is plus, like this. In the simply supported beam, only this much will be there. Now overhang is there means the lines are extended. More than that, nothing else is there. To draw this one, you should not take more than 30 seconds time. First time when I am explaining it is taking so much time, but in the exam it's like this. Without removing the supports at A and B, cut here, rotate. If you rotate like this, it goes up. But now if it rotates like this, red color line. Then 4 options will be given. One of the options you have to tick that. Okay. Now, if it another paper they have given, first simply supported beam we have studied, now overhangs. Next problem, I can put links here and attach some other piece. To that again link you put it some other piece you can attach. Simply extending the lines, but they are statically determinate structures only. So one such problem is like this. The beam shown in figure, next problem is, the beam shown in figure is subjected to a moving distributed load of 4 kilonewtons per meter width. Maximum shear force that can occur at just 2 RHS of Q is the beam they give you 2 minutes time. So actually you have to finish off in 1 minute time itself. Okay. So this is the problem. See, this is a P, Q, R, S. The distances are also given. We have the floating hinges. This is 5 meters, 5 meters, 20 meters, 5 meters, 5 meters. Now just to the RHS of Q means here. So preferably in 30 or 40 seconds time, you must draw the ILD for shear force at RHS of Q. This is ILD for shear force at RHS of Q. I will read now same thing without removing the supports at A and B means here without removing the supports at PQRS, that means 4 control points. Don't remove the support at P, Q, R, S. Without removing the supports at PQRS, cut the beam at RHS of A there. Now here cut the beam at RHS of Q and lift the beam such that theta Q is equal to theta R. This is your simply supported span 20 meters, length is 20 meters. So theta Q is equal to theta R is equal to 1 by L. That means 1 by 20. First you have to consider only this much portion, then you extend it. What is the difference between the earlier diagram and this diagram is earlier diagram you have done up to here only. Now it is extended up to S and Q with the two links. Some more links are added. Otherwise this and earlier one are same. Now don't remove the supports at PQRS, cut, rotate. First you see blue color one will see. If you rotate it, it will go up to here. This is only imaginary line, but actually just to the RHS of you have to stop. This value is theta Q is equal to 1 by L is nothing but 1 by 20. 1 by 40 we should not write because this is our supported span. Whatever extensions are there, that we will make it later. Theta Q is 1 by 20. This is also 1 by 20. So 1 by 20, this length is 5 meters. So 1 by 20 into 5, this value is 1 by 4. Having found 1 by 4, here there is this one. If this goes up, because of the floating hinge, P will remain as it is, simply it goes up like this. So this you join plus, so left portion is over now. So theta Q, then forget about it. Then theta R, 1 by 20. So 1 by 20 when you lift it, it will go up like this. 1 by 20 into L means 1 here, then it simply goes down like this. Then this is theta R is equal to 1 by L is equal to 1 by 20. Same as this one and this 1 by 20 plus here. This is minus. So 1 by 20 into 5, 1 by 4. This will become again 1 by 4. This is theta Q. Like this. So this is the influence line diagram for ILD for ILD for shear force at RHS of Q. Earlier problem, this problem same. Only thing is that extended values are the small two links. That links you are extending here and there. Blue color link, red color link you extended. This you must complete say in 30 seconds time. This ILD will tell you where you should keep the UDL to get maximum reaction at maximum shear force at RHS of Q. See here, this is positive quantity, positive quantity. So if the train goes and occupies the place up to PQR, let us say, keep the load up to here. You can ask the engine driver to drive up to R and stop. If he goes further right side of R, then that intensity of UDL into negative ILD I have to write, negative area, then net value will become less. So stop the engine at R. In this case, positive, positive, so we could do like this. This is a train. Supposing that you get positive here, negative here, positive here, then you should not break the train into pieces. First two compartments here, that means first two compartments here, then break it, then engine somewhere there. Not possible. Engine at one place, compartments at other places, not possible. It should be continuous. So positive, negative, positive comes. Then which positive area is more you have to see. Then ask the driver to move up till the end. You have to keep the positive UDL at the RS zone only, if at all this area is maximum. But in this case, no such issue because only 1 minute time is there. How to split the load, not necessary to deal. So positive area, put the load at PQR zone. Then you will get maximum shear force at RHS of Q. Then you may get a doubt that if you want to find shear force at RHS of Q, keep load here only. Why you are keeping here? Even if I keep load here also, there is a positive shear force at RHS of Q. This blue color, red color ILD is entire thing is for shear force at RHS of Q only. When the load enters the bridge here, shear force at Q is 0. And when the load is moving right side towards this floating hinge, shear force at RHS of Q is positive and that value is load into this ordinate. Load into this ordinate or load into this area gives shear force not at LHS of Q. It is gives you will get only at RHS of Q only because this ILD for RHS of Q. Other than that, no information you will get from this diagram. Wherever you keep the load, load into ordinate gives shear force at RHS of Q only. So now this, to get maximum reaction, you have to keep the load like this. Theta Q we know. Theta Q 1 by 20. This is also 1 by 20. So to get maximum shear force at RHS of Q, keep UDL over PQR only. Okay. So the ILD will tell where we have to keep it. So maximum shear force at RHS of Q. Intensity of load, how much is given? 4 kilonewtons per meter. This intensity is 4 kilonewtons per meter. So intensity of UDL into area of ILD under UDL. That means this triangle plus this triangle. Half, this base is 10 meters, height is 1 by 4. This is blue color area plus red color area. Half, base is 20, height is 1. So you will get 10, this also 4, this is you will get 5, 45. So first 30 seconds you must draw this diagram and decide where you have to keep the load. Then this calculation should be over in maximum of 1 minute time. First time when you are learning that without knowing Muller's principle, it will take a lot of time. But having understood what is the scope, how to save time, in the exam they don't go beyond this one. You will now complete, after completing our ILD classes, by inspection itself we will be able to say what is the answer. Okay, that means or by calculation without in the time of 30 seconds time, we will finish up the problem. No question takes more than 30 seconds or 1 minute time in structural analysis, whether in GATE or prelims exam. That is the only scope. Okay. Now, before we draw influence line diagrams for bending moment, let us see what sign conventions we followed in strength of materials. Briefly I review and go back to that. So, this is what you have learned in SM. Sign conventions for shear force and bending moment. For shear force, assume that you have a beam like this. This we take it as positive shear force. This we will take it as negative shear force. Correspondingly, the shear deformation you have studied like this. This is positive shear deformation. Okay, shear deformation is like this, and for this one, it will go up like this. The faces will not rotate. The axis only will rotate like this. Okay, this is negative shear force. This is shear deformation. In strength of materials, because of this shear deformation, the beams, they will deflect. In the deflection chapter, you have studied deflections due to bending moment only. Ea d square y by dx square is equal to minus m. Then deflections can also be caused because of the shear deformation, but being very less you neglected. Such shear deformations you cannot neglect if the beam doesn't have a solid web, and say gap is there, say two flanges are connected by lacing or battening, and if you bend them, then shear is predominant. Shear deformations also you have to consider. That means shear deformation means deflection due to shear also you have to consider and accommodate in our design calculations. So, this shear deformation you will consider in the design of steel structures, in the design of lacing, design of battens. Wherever solid web is not there, means Verendel trusses also web is not solid and it is discontinuous. So, there also you have to consider shear deformation. In RCC, deep beams, if your sir might have told you, in deep beams also you have to consider shear deformation effects. But in our ordinary strength of materials and structural analysis calculations, we neglect the shear deformation, this one and this one. And based on the shear deformation only, the positive shear force or negative shear force are taken. Okay. Next, for bending moment. This is positive bending moment you have taken, right? Because of this moment, it will sag like this. Sagging bending moment is taken as positive bending moment. If any moment acts like this, you will take it as negative bending moment. This is sagging bending moment, positive. This is hogging bending moment, you take it as negative. For any beam to sag, this is what should be there. You have a beam, let us say. For it to sag, left side clockwise or right side anti-clockwise movement should act. Only then it will sag. Section right side if anti-clockwise is there or section left side clockwise is there, those movements will force the beam to sag. If at all you have a sagging movement, a movement which causes a sag, we take it as positive bending moment. A movement which causes the beam to hog like this. To hog, section right side clockwise, section left side anti-clockwise should be there. Then it will hog. That means based on the deformation you fixed the sign. Based on the deformations, we fixed the sign. That's why these sign conventions are called deformation sign conventions. These are not equilibrium sign conventions. Equilibrium sign conventions means you will not worry about the deformations. You will be outside the structure, check whether it is at rest or not. If not at rest, with what acceleration it rotates or with what acceleration it translates. That is dealt by the equilibrium. Internal effects are bending moment, shear forces, and how they deform. Based on the deformation, you fixed the sign conventions. So much of difference is there between simply moment and bending moment. These sign conventions are called deformation sign conventions because they are based on deformations. They are not equilibrium sign conventions. There is a difference. Okay. So that's why moment and bending moment will be different. A movement can bend the member, then that movement is called bending movement. A movement can twist the member, then we call it as twisting movement. Just by changing the direction of a movement, supposing that you have a shaft like member like this, say, if any movement acts perpendicular to the longitudinal axis of a member, that means in this direction, you apply movement like this, say, it will bend. So we call it as bending moment. Instead of applying movement like this, apply like this along the longitudinal axis of the member. How to decide? When you turn nut and bolt system, when you turn the nut, it will advance like this along the axis. That movement will twist the member. Then we call it as twisting movement. Depending on the direction of the movement, just by changing the direction, the behavior of this member or the stresses developed in the member are totally different. That's why in strength of materials, theory of bending, theory of torsion, two separate units you needed to study just by changing the direction of the moment. Okay. So now here we are dealing with the bending moment only, not the twisting moment. So they are equilibriums, not equilibrium sign conventions. Now based on this one, you have a third sign convention also. Upward forces always produce positive bending moment, and downward forces always produce negative bending moment. Why like that? Assume that we have a structure like this, and only one force I will take it. Assume that we have an upward force here, upward force P. We are not worried about the reaction R, upward or downward. Okay. Some force P we have applied, we are interested only about P. Cut, remove it off, only P I want to discuss. Why upward forces give positive bending moment, we want to know. Due to P, I want to find the bending moment at this point, let us say. Your first task is you must go and stand there like this and look at the force. You travel from tail to the head towards the point like this. Section right side anti-clockwise. You see here, section right side anti-clockwise produces positive bending moment. How much it is? Supposing that if it is 1 meter, say, so P into 1. If it is 2 meters, P into 2. So positive bending moment, that means sagging bending moment of P into 2 meters. I don't want to find bending moment here, I want to find bending moment here, say. Then your first task is to stand here. Stand here, look at the force. travel from tail to the head towards the point, like this. Section left side clockwise. See here, section left side clockwise produces positive bending moment. That means this produces positive bending moment. P will give positive bending moment about this point. That means whether you stand here or here, wherever you stand, this upward force always gives positive bending moment. Same thing we have written. Supposing that as a second example, see, net movement may be different. This produces positive bending moment, this downward reaction may produce negative bending moment. If negative bending moment magnitude is more than positive bending moment, so there can exist a net negative bending moment. Maybe it is hogging, but due to this alone, there must be positive bending moment. So is the case here. Supposing that there is a downward force P. I want to find bending moment here. Stand there, look at the force. Tail to the head towards the point. Section right side clockwise. Section right side clockwise. It produces negative bending moment here. I want to find bending moment here, say. Stand there, look at this force. Tail to the head towards the point. Like this. Anti-clockwise. So section left side anti-clockwise. Section left side anti-clockwise. Negative bending moment. So whether I stand here or here, this will always give negative bending moment. So first task is you have to stand here, then find the bending moment. Now you see, I want to find bending moment somewhere here, say at A. This distance, let us say 3 meters. What is the bending moment due to P at A? Bending moment due to P at A. How much? P into 3 we cannot write, because bending, once you use the word bending moment, that force P must bend someone. In air, whom will it bend? Nobody is there to be bent. First task, assume that at A I asked you to bend it, in the case what we have done earlier, here also. Your first task is to stand. Stand at A. Immediately what will happen? We will fall down. When we are falling down, whether this fellow gives positive bending moment or negative bending moment, you cannot worry. So bending moment cannot exist because there is nobody to bend at A. But external rotational effect, simply rotational effect, how much means P into 3. It may not bend anyone, may not twist anyone. Simply movement means that external rotational effect of a force. If at all it bends, then we say that there is a bending moment. If at all it twists, then we call it as it is twisting the member. So bending moment due to P at A. Cannot exist because there is no member to bend at A. But in trusses chapter, we have, if you remember vaguely, method of sections when you cut it, you found moments of all force about some point in air. Those some points in air, when you are finding the moments, they are not bending moments, they are simply rotational effects. Such rotational effects of all forces must be zero. Otherwise, about that point, that body as a rigid body, it will rotate. So, but the external rotational effect of P about A will exist. That is, moment of P at A is equal to P into 3. That's all. But you cannot write here bending moment because it is not bending. Simply moment means external rotational effect. Now, having got that clarity, the difference between external rotational effect, that is moment, and bending moment, Now we solve the problems. How to draw influence line diagrams for bending moment at any section. Now let us see concept 4. ILD for bending moment at any section C. Again in simply supported spans. SS span means simply supported span. Now let us see. Assume that we have a beam like this. A, B, somewhere C is here. This distance let us say A. This is say B. Again there is a ground you have to visualize. Ground. First we will take strength of materials concept here also, then we will see how to save the time. When the load is exactly at A, what's the bending moment? Because load is at A means the direct transfer of load to the support happens. So VA is 1. So bending moment at C means it is not at all taking the load. So bending moment is 0. They balanced themselves. When unit load is at A, bending moment at C is equal to 0. That means the influence of 1 on bending moment at C is 0. That means the influence ordinate is 0. The influence is 0. The ordinates that you are showing, they are the influences of the unit load on bending moment or reaction or shear force. Okay, so bending moment at C is 0. Next, when unit load is at B, what's the bending moment at C? Again 0. That also we know. When unit load is here, we know. When the unit load is at C, also we know. When unit load is at C, bending moment at C, we know W AB by L. Now W becomes 1. So you will get AB by L. What it means is the influence of 1 on bending moment at C is AB by L. Influence of 1 on bending moment at C is AB by L. So 3 points, if you know the influences, you can connect them. Because of the point load, we know the bending moment variation is linear. So you can directly connect it as a linear variation. So this is the meaning of that. It means that influence of unit load on bending moment at C is AB by L. That is the meaning of getting AB by L here. Now, so draw ILD as shown in figure. So draw ILD for bending moment at C as shown in figure. Now, again Your allotted time is 1 minute. So much story you cannot write in the exam. If it has overhangs, suppose, then overhang also you have to keep the load and check what's the bending moment. It will take 3 minutes to 4 minutes time. So we take again the help of Muller. For that, first let us see what are the characteristics of influence line diagram. Note 1. Characteristics of ILD for bending moment at C. First point is this one. See, first we'll calculate here theta A. Tan theta A is equal to opposite side by adjacent side, AB by L by A, you will get B by L. Then theta B, opposite side by adjacent side, AB by L by B, you will get A by L. Now, this quantity is AB by L. Now, if I extend this line, if this theta A is B by L, this is also theta A, B by L. If this is theta B, this is also theta B. So, B by L plus A by L, A plus B by L, that means L by L is 1. So, this total quantity theta becomes 1. These things will write there. First point is tan theta A is approximately equal to theta A is nothing but AB by L by A. So, you will get B by L. Tan theta B is approximately equal to theta B, AB by L by B. So, you will get A by L. Then theta is equal to theta A plus theta B, B by L plus A by L. One you will get. Okay, this is what your observations. Then second one from Muller. What Muller said was, now coming to this diagram. We want to get this influence line diagram without this much story. We have only say 10 seconds time. What he said was, if you want to draw ILD for bending moment at any section C in a simply supported beam or any beam without removing the supports, assume an imaginary hinge at the point where you want to draw ILD. So, in this case C. So, assume an imaginary hinge at C. Assuming an imaginary hinge at C means releasing the moment at C. If you want to draw ILD for reaction, release the reaction, means remove the reaction, lift it by 1. If you want to draw ILD for shear force at C, release the shear force. Releasing means cutting it. Then if you want to draw ILD for bending moment at C, release the moment. Releasing the moment at some point means assume a hinge there. We know bending moment is 0, our moment is 0. So assume an imaginary hinge at C and lift it by an amount of AB by L. Then automatically theta becomes 1. Then the deflected shape of the beam itself is the ILD for bending moment at C. So assume a hinge and apply unit rotation. To apply unit rotation, it must be lifted by an amount of AB by L. Only then theta becomes 1, segments will be straight line. If you keep here only and rotate, they will get a curved one. As I told you, in a statically determinate structure, assuming an imaginary hinge implies that it becomes unstable. Unstable structure, if you want theta to be 1, you have to lift it by an amount of AB by L, automatically theta becomes 1. Same position, if you keep it and rotate, you will get a curved one, which is not possible. Curve it cannot take because it is unstable structure. So this is what happens from Muller. What we have to do is, without removing the supports at A and B, assume an imaginary hinge at C, within brackets, that is release moment at C, and apply unit rotation. Within brackets, to get unit rotation, the beam, the hinge must be lifted by AB by L. Okay. Then the deflected shape of the beam itself is the ILD for bending moment at C. This is the process. Okay. Now, this ILD will tell us how to keep the loads to get maximum bend moment at C. Case one by one I will discuss. If a single load is moving from left to right, to get maximum bend moment at C, you must keep the load at C only. Load into maximum ordinate, so maximum bend moment at C will get. If two loads are moving on the beam, then greater load at greater ordinate, lesser load on the less slope side, that means where span is more. This is slope is mild, here steep slope is there. So if you keep the load here for same distances, here ordinate will be less, ordinate is more. So keep the load on the right side, lesser load on the right side, greater load on the C itself. Then you will get maximum bending moment at C. That is one load, two loads are over. If UDL shorter than the span is moving, this is 10 meters, UDL span is only 3 meters. Then you must adjust the load near center such that area of the trapezium must be maximum. To get the trapezium area maximum, you must keep the load such that load on AC by span, load on CB by span. In that ratio, you have to cut the UDL and keep the load. That means whatever ratio C cuts the span, in the same ratio, C must cut the load also. Then you will get maximum bending moment at C. If at all UDL longer than the span is moving, span is 10 meters but UDL is 20 meters say, that possibility also will be there. If you see you are moving in a train length let us say half kilometer, then bridge length is only say 100 meters. Then the train goes say, half of the train will be on the bridge, half the train will be on the ground only. So like that happens. So if at all load UDL is longer than the span, then keep the load on the span completely, remaining load will be on the ground. Then intensity into total area you will get maximum bending moment at C. Then if at all more than 2 point loads are moving, 3 or 4 loads are moving, then average load on that condition we call it as load on AC by span AC, that we call it as average load. Okay. Now when the more than 3 point loads are moving, average load on AC must be equal to average load on CB. When the loads are moving, different magnitudes can be there. Exactly average load on AC may not be equal to average load on CB. So what we do is one by one loads we will move them. First keep all the loads here, zero load here. So average load on AC is maximum, average load on CB is 0. So let one load pass. So here average load slightly increases, slightly decreases. Next load, one by one when you are passing. At one stage average load on AC will be equal to average load on CB, one possibility, or average load on AC may be less than average load on CB. That is the second possibility. So under what load, whether they are equal or less, we will see. Correct definition is under what load the change of sign happens, either equal or less than. Happens, you have to see that load should be kept at C and all other loads you have to adjust. Then you will get maximum bending moment at C. Okay. So these are the possible cases. Then absolute maximum bending moment means they will not specify the section. You select the section wherever you want. Then I wanted maximum bending moment. Then instead of C, where is the maximum bending moment in simply supported beam? Somewhere near center. So all these things should be kept near center, you have to adjust the loads. Then what you get, the bending moment is called absolute maximum bending moment. So these are the things. These things one by one we will discuss with the help of the numericals. Now first problem we will take single point load not required. Any example, load into AB by L over. If two loads are there in GATE or PRIMS exam, one load they will not give because SM concept itself you will use it. When two loads are there, then you have to draw ILD only. Then we'll see how we have to simplify. Okay, now let us see the numericals. Two wheel loads of magnitude 10 kilonewton and 5 kilonewton spaced 2 meters apart crosses a simply supported span. Two wheel loads is a set. Crosses a simply supported beam of span 10 meters. Maximum bending moment at a distance of 4 meters from left support is. Now you see, we have a simply supported beam AB. This point let us say C. Now he is asking at a distance of 4 meters from left support. So A is 4 meters, B becomes 6 meters. Now we know how to draw ILD for bending moment at C. Without removing the supports at A and B, assume an imaginary hinge here and lift it by an amount of AB by L. This height is AB by L. This is your ILD for bending moment at C. AB by L means how much? A is 4 meters, B is 6 meters, length is 10 meters. So you will get 2.4 meters. In this case, influence coefficient for bending moment has units of meters. For reaction, for shear force, no influence units, they are dimensionless. So this is AB by L, nothing but 2.4 meters. So now we have two loads are there, 10 kilonewton and 5 kilonewton. Greater load at greater ordinate, that means here 10 kilonewton, lesser load here, this is 5 kilonewton, spaced 2 meters apart. Why right side, why not left side? We'll see with the help of this one itself. This is 6 meters. For 6 meters 2.4. This is 4 meters. For 4 meters, 6 into 4, you 2.4 you are getting. 4 into 4, 1.6 meters. Now you see, if at all I keep here, let us say, at 2 meters distance. For 4 meters, 2.4, 2 meters, because this length is only now 2 meters, 1.2, 2.4, 1.2, 0. See, 1.2 meters influence is less than this one. So this is steep slope. So by the time you move by 2 meters, so much decrease in the ordinate will happen. So we should not keep this less span side. Greater span side, if you keep it, span is more. So this is also ordinate will be more. So to get maximum bending moment at C, you must keep the loads here. So to get maximum bending moment at C, keep the loads as shown in figure. Then influence of 10 kilonewton on bending moment at C is 2.4 meters. Influences are in meters. So load into influence, you will get bending moment at C. We know bending moment units kilonewton meter. So if this is kilonewtons, this must be meters. It's not drawn to scale, it is only influence ordinate. That ordinate if you multiply, you will get the bending moment. So influence of 10 is 2.4 meters, influence of 5 is 1.6 meters on bending moment at C. So as shown in figure. So maximum bending moment at C. So 10 into its influence is 2.4 meters plus 5 into 1.6, 24 plus 8, 32. This is you will get maximum bending moment at C. When they specify the section, at that section only you have to find the maximum bending moment. But that may not be absolute maximum bending moment. Absolute maximum bending moments occur in near center. As you have studied in strength of materials, in simply supported beams, maximum bending moments happen near center. But I don't want at center, I want at some other section near support, I want say. Then you have no choice. At that section only you have to find. He is not asking absolute maximum. At some particular section, what is the likelihood of maximum bending moment that can happen at that section only? Okay. At some other section, there may be more maximum bending moment, but we don't want. So he says now, at C only I wanted maximum bending moment, you adjust the loads the way you like. That's what. If they don't give C section, at 4 meters word is not there, then you must select a section of our choice. Then we will select near center. How to select, we'll see again in the next classes. Now this is the maximum bending moment here you will get.